Hello, so in this video, in this final part of this chapter to do with forces, we're going to be looking at something called pulleys. Okay, so I've got some examples of pulleys here, just to illustrate the essence of what a pulley is. Okay, so look at this diagram here. So we've got this person here, this kid, pulling up a box on the other end. So the idea is with a pulley, I've got this string, right, and it connects two different objects at either end of the string. So here at one end I got the boy here, then at the other end I got the this piece of wood, okay, this box, okay. And so as you can imagine, as the person pulls at one end of the string to pull it back, the boxes are going to go up as a result of that, right? And so that's the idea. So we have two objects connected at either end of the string. The string goes through this pulley machine here. This is the pulley that allows the string to move. So it goes one end or the other. So one object goes up, one object goes down, and vice versa, right? Let's have a look at this example. This is more what we're going to be looking at. So here, if I just add, let's say, a little ball on one end here, and so I got the ball on one end on the left, and on the right, I got this massive weight. Okay, this iron weight. Now think about it. Where would things move? Right. Well, hopefully you can visualize that this little ball here is going to be much smaller compared to the weight here. So what's going to happen is the weight is going to want to come down. Okay, it's going to want to go down due to gravity, due to its mass, which should mean if one goes down, so that the iron here, this little weight, if that goes down at one end, then the ball has to go up as a result of that, because it's all connected by the same string. Okay, so if one end goes down, so again this little weight goes down, the ball goes up. Okay, hopefully you can visualize that, right? So one more time, the weight, this weight is bigger than the little ball here I've circled, so the weight will come down, so that'll force the ball to go up at the other end. Okay, so that is the main premise. Okay. That's a pulley. Now, again, this video, like with the last video, will be split up into two parts, because you need to know how to deal with two distinct type of pulleys. Okay, but we're going to be looking at one that's in the air, like this example, and we're going to be looking at another type of pulley where it's on a table. Okay, so it's on a surface, but we're going to be dealing with pulleys like this first. Okay, now. So that's the idea of a pulley. Now, the other thing you need to know is, again, if we have two objects connected by a pulley like this, so again we have this ball and this weight, what you need to know is we're going to be dealing with inextensible strings. Okay, like with the last chapter, inextensible here is, I'm going to say, what I'm going to say is, as long as a string connecting two objects is inextensible, so this string that's connecting the two objects in a pulley, if that string is what we call inextensible, which we looked at last time, that means the two objects will move with the same acceleration, which you should be familiar with again from last time. So when we looked at a car that's towing a trailer which is being connected by some inextensible rope, that inextensibility means the car and the caravan move with the same acceleration, but what it also means is they will move at the same speed and distance too. Okay, so what do I mean by this? Well, as long as this string is inextensible, if I take these two objects here, again, let this little big weight here we want to move down. If the weight, let's say, moves 5 meters downwards, then as the ball here on the other side will move up, if the weight moves down by 5 meters, the ball will move up by 5 meters. So if one object goes down, then the other object has to go up at the same amount. Okay, and their speeds are the same as well. Okay, as long as they're connected together by an inextensible string. Okay, right, so that's going to be a key thing we're going to be dealing with. The last thing, which is a bit of a recap actually, so cast your minds back to when we looked at constant acceleration in the last chapter, where we looked at things in free fall, so they're moving up and moving down due to gravity. So let's say I have a particle or some object that's been shooted up, right? It's been shooted up and it's going against gravity, right? So remember, the acceleration with gravity is g, and g is 9.8, right? Usually 9.8, or sometimes we round it to whatever we want, but that's 9.8. Okay, so it's going against gravity. If the particle is moving up against gravity, then let's say the particle initially is at speed, let's say 10, right? The speed we're going to have to go down, right? The particle can't just go up forever, right? Because it's going against the gravity that wants to pull it down. It's going against its weight. So what would have to happen is at some point down the line, it can't go up any further. So it maybe at this point here, it'll then have no speed. Okay, so it's going to come up to its maximum height and it can't go any further because there's no more speed left. Then it'll have to come down due to gravity. So this distance in particular is the greatest height. Okay, hopefully that makes sense again, where if a particle or an object is being shooted up against gravity, then it can only go up so far until then it has to come back down. And the maximum height is when it ends up at 0 speed. And then at that point, it has to come back down again. Okay, so we will be using that with some questions as well. So make sure you are aware of this. Okay, so that's just some things we'll be using. But actually now, let's just have a look at some questions. Okay. All right, so we've got this question here. Now, we're told particles P and Q of masses 2m and 3m are attached to the ends of a light inextensible string. Again, it's inextensible, so their motions will be the same for the both particles. The string passes over a small, smooth, fixed pulley, and masses hang with the string taut. Taut basically means inextensible. It means it has tension. Okay, has a lot of tension, but taut is basically inextensible. Anyway, the system is released from rest, and in part A wants me to write an equation of motion for P and for Q. Right, so as always, we want to kind of illustrate the situation, draw a sort of diagram, right? Now, this diagram, again, this is one type of scenario you need to deal with. It will be virtually the same every time. It'll be the same sort of diagram every time. Now, firstly, we have a pulley. Again, I'm going to draw a pulley by this sort of circle, right? And then what I've got going on is everything's been connected by a string. If I do that in, say, blue, right? So what's going to happen is I have a string at one end and it's going to thread through the pulley, right? Like this. Hang on. And then it's going to thread at the other end. Okay, so that's the idea. So the blue is the string there. Okay, so the idea is that piece of string is going to thread over the pulley. Okay, right, and so then at either end of this string I have my two particles. So P, which is 2m, I'll draw P here. So P is 2m, lots of kilograms. And Q is 3m. So Q is going to be a bit larger than P because it's going to be 3 lots of m. So Q is larger than P because P has mass 2m, but Q is mass 3m. So it's slightly larger, okay? So with that in mind, where would you expect the motion to be? If Q is heavier than P, you'd expect Q to go down, right? And P to go up as a result. Because Q is going to tug everything down, and P, because it's lighter, it's going to go up as a result, okay? So hopefully you can visualise that. So therefore the accelerations then, the accelerations are going to be in opposite directions. So because Q is going down, the acceleration is A, okay? And again, it's not G. The acceleration will not be just G because Q is not just falling through the air, it's attached to rope. So there's more forces acting on it than just its weight falling down, okay? So it's just I don't know what the acceleration is, I'm going to call it A. Likewise, P would also have the same acceleration, but in the other direction, okay? Why the same acceleration? Again, remember, the string is inextensible, which means the same acceleration and also the same speed and distance they travel. Anyway, right. Now, in terms of forces, again, both objects are going to have its weight trying to pull it down. While the weight of Q, so remember, weight is mass times G, while the Q is mass 3m, so it's going to be 3m lots of G. Okay, that's its weight. Likewise for P, it's going to be 2m lots of G. Okay, now, at this point, I could say G is 9.8, but at this point, I think it is a bit better to just leave things in terms of G. Because it does make things a bit more simple, okay? Just remember that G is just a number, okay? I'm not going to just convert to 9.8. I can do, but you'll see a lot of questions as we go on. It will be a lot easier to just leave G in because G's cancel and stuff like that. But anyway, so that's my weight, okay? So hopefully with me here. So I've just drawn my string, my blue string that goes over the pulley like that. And have then at either end I have my two sort of weights, my particles P and Q, and I've added on their weights, pulling them down, okay, and their accelerations as accordingly. So Q is heavier, so it's going to go down, and P is lighter, so it's going to be pulled up by the same string. Right, okay, now there's one more force. Now it's string, so there has to be tension involved, okay. So, what we're going to do with the string, obviously there's going to be tension because the string is being stretched at either end. At this end, at the right, by Q, the string is going to be pulled down. And, and the same for P actually, because they're both going to be pulled down because of their weights. So, at either end of the string, if I do a dotted line there, Q is going to have a tension pulling it up, okay, because the string doesn't like being stretched, okay, so it doesn't like being stretched due to the weight of both of the particles, right? So the string is going to oppose the tension either way, okay? So hopefully that made sense with the tensions there. So again, there's two lots of tensions at either end of the string by each particle, okay? That's going to attempt to pull the things upwards to counteract the weights pulling the objects downwards, okay? To resist the stretching downwards. Okay, but that's not all. That's all the forces on the two particles, but the pulley itself has its own stuff going on. Now, we don't normally consider what happens to the pulley, so the forces at the upper end above this dotted line that affects the pulley. We don't normally care about it, but sometimes you will be asked. And actually, we're asked in part D to consider forces on the pulley. Anyway, so what's happening at the pulley then? Well, the pulley isn't in the air, right? What you don't see here is the pulley is actually also attached to something else, right? To make it hang, right? So it might be on some sort of ceiling. And so the pulley is actually being pulled upwards by some other force, okay? I don't know what it is. We don't care about the force. Again, I don't care about what happens to the pulley, but there's something going on. The pulley's being pulled up by some other force, okay? So it might be hanging on the ceiling, okay? Or something like that. It might be on a hook or something like that. So there's some force that's trying to pull the pulley up to oppose all of this weight and stuff trying to pull the pulley down, okay? So there's a force up, but again, the pulley's being stretched. Well, the pulley's being pulled up, so the string is being stretched, right? And so it's being stretched upwards. The string is being stretched upwards near the pulley. So actually, again, the string wants to resist the stretching at either end. So by the pulley, the tension goes downwards. Okay, and there's tension at either side, okay, of the pulley there. Okay, so you don't see that, but the pulley's been held in place by some upper force. Okay, I don't know what the force is, but it's been held up. So the tension acts downwards to resist this stretching upwards by the pulley. Okay, and so I want to make it clear. These are the tensions by the pulley. These tensions are by the particles, okay? Which are separated by this dotted line I've done here, okay? So all of this is to do with the pulley. But we don't really focus on that. We'll just be focusing on the lower half, okay? What's going on by the particles. Okay, that's literally all the forces acting on it, okay? That we are modelling with here, okay? And so the final thing I just want to add on, just to really explain what's going on to help understanding. Usually with these questions, you're told the system is released from rest. Obviously, that means that P and Q initially have no speed. Now, what do we mean by that? Well, what's going to happen is, if it's been released from rest, that means it is put at rest initially. How that is done is, you can imagine maybe someone with both hands are holding P and Q by the hand. That basically forces P and Q to stay still. So you can imagine, before we start off this sort of mechanics, right, before we want it to start, right, the thing's moving down and up, you can imagine the blocks P and Q, right, they're being held physically, perhaps by someone's hands, to stop them moving down and up. Because what will happen is, once you stop holding P and Q, right, if you just let P and Q move naturally, Q will then start to move downwards by its own accord, and P will want to move up by its own accord, right? Because Q is heavier, so it's going to want to move down, right? So when it starts at rest, that essentially means P and Q are being held to stop moving, okay? And then once we so-called release the system, that means we no longer stop holding P and Q, right, to stop it moving. We just let P and Q move by itself, okay? So that's everything, okay? Now, let's have a look at the question then. It wants me to write down an equation of motion for the particles P and Q. Now, equation of motion literally is another word or phrase for just F equals ma. Okay, we can this equation can be just also means equation for motion. Okay, so in other words, write down F equals ma for both particles. Okay, so firstly, particle P. If I use F equals ma for particle P, so particle P is here. That's all of particle P. So if I resolve upwards then, which is where particle P is going, it's accelerating up. So the upwards force, well, P, the upwards force is the tension in the rope pulling it up. And that's going to be taken away by the downwards force, the weight, okay, the weight pulling it down. So to take away 2 mg, that's going to equal then ma. So the mass is 2m, so it's going to be 2m, lots of the acceleration a, okay? Now, it looks very complicated, this equation looks quite weird. But there's nothing more we can do here, okay? Not much we can do. There's a load of missing variables, right? T, M, and A. But we have to live with it, okay? And then if you do the same for Q, well, Q, if we look at just Q now, so this is what's going on at Q. Again, if we resolve downwards then, because Q wants to move down, again, due to being heavier out the two particles. So what's pulling it down is 3mg. Take away the tension in the rope that's trying to pull it up. So the tension up here. And that's going to equal Ma. Okay, well the mass of Q is 3m times A. Right, so I end up with these two equations. So T minus 2mg is 2ma. And 3mg minus T is 3ma. Okay, so that's part A. That's the equation of motion. That's F equals ma for both particles, okay? Now, that's pretty much the same process every single time, these questions, right? That's what you're going to want to do. You want to use F equals ma on both particles there, okay? Then it says in part B to find the acceleration of each mass. So we need to find the acceleration A. So we're going to need to look at these simultaneous equations. Now, we're going to need, well, they are simultaneous equations. We're going to need to solve them. So you'll see with this, again, that we're going to need to solve a bunch of simultaneous equations with these sort of questions, okay? So again, if I call this equation 1 and equation 2, so if I want A, if I want the acceleration, I'm going to need to probably get rid of T, right? T is probably a good one to get rid of. Now actually, I'm adding T in the first one and taking away T in the second one, right? So if I just add the two equations, so this is what I've got going on. T minus 2mg is 2ma. And then minus T, add 3mg, is 3ma. If I add these two equations then, so I'll just restate the two equations I've got in part A. If I add them, I get rid of the T's, right? Because then T take away T is 0. Well, minus 2mg add 3mg is just mg. And then that's going to equal 5ma. Okay? Therefore, 5ma is mg. So A is going to be mg over 5m. Well, the m's cancel, so I'm just left with g over 5. Okay? So A, the acceleration is g over 5. Okay? Right. Again, I could just substitute g as a 9.8 into it, but I'm going to leave g where it is. Okay, it's kind of like leaving it in exact form. So I'm going to leave g, and I'm going to leave it as g over 5. I'm not going to try and sub in g as 9.8 yet, unless I really have to. Right, okay, so that's my acceleration, just solving that simultaneous equation. Then in part C, it wants me to find the tension. Or again, if I go back to my equations then, if I substitute A here, right, g equals 5 into either equation here, I can get T. So if I substitute it into the first one, let's say, if I sub A equals g over 5 into the first equation, I'm going to get T, take away 2mg, it's going to equal 2ma. So it's going to be 2m lots of A, which is g over 5. Okay. So T take away 2mg, if I expand that bracket, I'm going to get 2/5, right? 2 over 5 mg. When that actually both terms are mg, right? I'm just adding, I can just like collect the like terms. So T is going to be 2mg, add 2/5 mg. 2 add 2/5 is 12/5. The 12/5 mg there, okay? That is my tension there, and that being newtons, right? And my acceleration is g over 5. And so that's my acceleration and my tension. Okay, it's pretty much going to be that sort of method all the time, pretty much every time with these sort of problems with pulleys, okay? And again, it looks quite scary in a way, because you've got loads of unknowns, like you've got M's, you've got A's, you've got T's, you even got G's floating around. But don't get bogged down by the variables, by the letters. They're all just numbers. All of them are just numbers. So just do the same process of solving simultaneous equations using F equals ma in the exact same way we've been doing. And don't try to get too concerned about all the weird letters floating around. It all works in the same way. Okay, there we are. So that's my expression for T and A. Then it says in part D to find the force exerted on the pulley by the string. Okay, so if I now consider the pulley in its own right, I'll do part D here. Now it wants the force exerted on the pulley by the string. So what force is created by the string onto the pulley? Well, the string creates these tension forces. Now these are the forces on the pulley. Okay, these are the forces caused by the string onto the pulley. These tension forces going down. Okay, so the force by the string caused by, or exerted by the strings, by the string, are these two tensions. Hopefully you can see that here. These two tensions are either side of the pulley. So it's going to be 2T. Okay? That's literally it. Okay? And again, that'll be the same every time. Okay? These two tensions either side of the pulley that tries to resist the force above the pulley, trying to pull the pulley up. Okay? So these two tensions are the force created by the string. Okay? So the tension forces. So if I work out 2 times T, well, we worked out tension in part C. So it's 2 lots of 12 over 5 mg. So if we work that out, that's simply 24 over 5 mg newtons there. And there we are. Then in part E, again, this is where it actually can get a bit more confusing. Find the distance moved by Q, so this particle Q, how much it moves in the first 4 seconds, assuming that P does not reach the pulley. Okay, so as we discussed, Q is going to want to move downwards. Okay, now we want to work out how far it moves downwards in 4 seconds. So let's say it moves this distance, right, in 4 seconds. Okay, so this will involve suvat, right? So suvat. Well, are we given any other information? Usually, yes. Usually you'll be told the system is released from rest. That means all the particles, all the objects start with velocity 0. So speed is 0. That's what rest means. So that means Q initially, before it moves down, right, has no speed. So speed is 0. Okay. And then obviously after 4 seconds, it will then have some speed V. Okay. But I don't really care about the final speed because it's asking me for the distance. So that's what's going on. And again, the acceleration would be A. Actually, we can just add that on now. We know that A is G over 5. So I can add that onto my diagram. I can fill that in. So G over 5. Right. So there we are. So if I use suvat on this then, for suvat, well, the distance, how far down it moves, that's what I want to work out. U, the initial speed is 0, so U is 0. V, again, I don't care about the speed after 4 seconds. A, as we discussed, the acceleration is G over 5. And the time is 4 seconds. So which formula excludes V for my suvat? Again, you are given the suvat formulas, but that one is S is ut at a half AT squared. So therefore S is 0 at a half of G over 5 over T squared, so 4 squared, which would be 8/5g. Okay, meters. I guess at that point you could say g is 9.8 if you wanted to. So then s is going to be 8/5 times 9.8, which should be 15.68 meters. Okay, so the distance is 15.68 meters. That's how far Q moves in the first 4 seconds, right? So it starts from rest. So again, you can imagine it being held physically by like a hand or something, so it doesn't start moving down by itself, but then the person takes the hand off and then Q just starts to go down by its own accord. After 4 seconds of that, then the distance it goes down is this 15.68 meters. Okay, then in part F, it wants me to state how I've used the fact that the pulley is smooth in my calculations. Okay, so again, another modelling assumption you need to know, which we went over in the first chapter, but again, we're going to see in action here. We've already seen that what the string being light and inextensible means. The string is light, which means there's no mass from the string, and the tension is the same throughout the string. Inextensible means the string has, again, the 2 particles attached to the string have the same acceleration, the same motion. But what we also need to consider is the pulley is both smooth and light. Well, light is quite easy. Again, it means no mass. So the pulley, if it has no mass, the pulley doesn't exert a weight, okay, because there is no mass. So there's no weight coming from the pulley. But also, the pulley is, as well as light, it means it's smooth, which again means no friction. And no friction in particular when the string passes through the pulley in this way, okay? So when the tension is moving through the pulley on top of the pulley here, so the blue rope, right? As the blue rope moves through the pulley at the top here, there's no friction caused, okay? It's completely smooth, which means there's no additional tension needed or no change in the tension on either side of the pulley to overcome friction force. So that means the tension is the same on either side of the pulley. And what that ultimately means is that the tension in both P and Q are equal. Okay, so that's what it means for the pulley to be smooth. Okay, so it's smooth, which essentially means the tension forces. So again, if I remind you, the tension forces on the left side is the same as the tension forces on the right side of the pulley. The tension is exactly the same all throughout the system. Okay, and there we are. Okay, so we've got this question here, and actually now they've given us a diagram. Okay, so here we're told 2 particles P and Q have masses km and 3m respectively, where k is less than 3. Now, before we go any further, why is that significant? I'm told k is less than 3. Let's think about it. P is mass km and Q is mass 3m. If k is less than 3, that means P has less mass than Q, right? Hopefully you can see that. So Q is heavier than P, it has more mass. So Q is going to want to move down, so the acceleration will be downwards at Q, right? Likewise at P, then it will want to move upwards, okay, as a result, so the acceleration will be up, okay? So we can use the information there to work out where things are moving based on how heavy they are. Okay, because the heavier particle will want to go down, okay, because its weight will be more significant. Okay, so that's that. The particles are connected by this light and extensible string. Again, if it helps to visualise, if I do it in blue, it's a single string here. So if I do it in blue, it's this string here that goes through the pulley. Oh. And then to the other particle there. That's what's going on, okay? And obviously this circle here, that's a pulley, okay? So we're told they're connected by light inextensible string, which passes over a smooth, light fixed pulley. The system is held at rest. So again, initially, we're not allowing P and Q to move. We're literally holding them fixed tight. Say like both P and Q are held by hands, right? Someone's hands. That'll just stopping them from moving by their own accord. Okay, because obviously Q will want to move down and P will want to move up. We're stopping that from happening until a certain point. Anyway, so they start at rest. The hanging parts are P and Q. They're above a horizontal plane, which means they're above a floor, a horizontal floor like that, okay? The system is released from rest, and then after release, Q goes down, as expected, with acceleration a third of G. So actually we know the acceleration. Now, if that's acceleration at Q, if it's an extensible, then that's also the same acceleration in P, but the other way, right? A third of G. Okay? So we know the acceleration in terms of G. Now, it wants me to calculate the tension in the string as Q descends. So again, we need to add on our forces. So at P, firstly, the weights are going to be pulling both down. So P, if it's mass Km, its weight is Kmg. And the weight at Q, well, if it's 3m, it's going to be 3mg downwards. Hopefully you can see that awkward diagram position. Okay, but that's the weights. Then the tension, again, will oppose that stretching downwards either end. So we have two tensions here and here. That's all my forces I care about. Again, there'll be more forces on the pulley. So at the pulley, obviously there's going to be a hidden force pulling the pulley up, and then tensions downwards to oppose that by the pulley. But I don't care about those forces. Okay, I don't care about them. Now, they want me to calculate the tension, okay, as Q descends. So if I consider perhaps F equals MA on Q, right? So at Q, if I do F equals MA, so if I resolve downwards, because Q is going down, well, the downwards force is the weight 3mg. Take away the tension going up at Q, that's going to equal MA. Well, the mass of Q is 3m, so 3ma. But obviously we also know the acceleration is a third of G. And so if we simplify this, we get 3mg, take away T is mg. Right, 3 times a third is 1, so mg there. So actually T is going to be 2mg, right? And so there we are, 2mg newtons. Now, again, that's not ideal. We have this unknown m in the answer, and we're deciding to leave g in as well, but that's the tension there, okay? Then it says in part B, show that K is 1.5. Well, again, it's a very good idea to consider F equals ma for both particles. So we already did it for Q. Let's do it for P and see what happens. So if I do F equals ma for P, now P is going up, okay? P wants to go up. So if I resolve upwards, well, the upwards force, again at P, the upwards force is the tension pulling it up. Take away the weight of G of P, the weight is Kmg going down. That's going to equal ma. Well, the mass of P is Km, so it's going to be Km lots of A, where the acceleration is a third of G, right? A third of G. And so if I simplify it then, well, we get T minus Kmg is a third Kmg. And okay, and then we could simplify it a bit more because we have Kmg in both terms. So T equals, well, 1 lots of Kmg and a third lots of Kmg is 4/3 Kmg overall. There we are. Now, we also know what T is. Well, we know an expression for T thanks to Q in part A, right? We can sub this in. So 2mg is 4/3 Kmg. Well, actually, if we want to solve for K, if we divide by mg to both sides, to get just k on its own, to solve for k, we get 2 equals 4/3 k. But what do you know? Despite not knowing what m is, and even despite despite not subbing g in for 9.8, we can still work out exact numbers for missing numbers, right? So we can solve for k now quite clearly. If we divide by 4/3, so 2 divided by 4/3, we get k to be 3/2, or 1.5. Now, if I recall, yes, the question wanted me to show it's 1.5, so we're on the right track. Then in part C, it wants me to state, and actually I can add that on, kmg 1.5 mg. There we are. Then it says in part C, state how I've used the information that the pulley is smooth. Again, the pulley is smooth, which ultimately means... actually, I'll do it up down here. The pulley is smooth, which ultimately means, well, the tension is the same at either side of the pulley, which also then means the tension in both the particles, so the tension at P and Q are equal. The tension will be the same all throughout the pulley, all throughout the string there. Okay, then it says, and now this is where it gets hard. Harder, I guess. After descending for 1.8 seconds, Q. So I'm going to just temporarily get rid of all these annotations, right, to make it clear what's going on here. So I'm told after descending for 1.8 seconds. So remember, Q is going down, right? It wants to go down. After descending for 1.8 seconds, so the distance is, I don't know, but I know the time is 1.8 seconds. Now, after 1.8 seconds going down, Q reaches the plane. So it reaches the floor, okay? So the plane is basically the horizontal floor, okay? There we are. Hopefully you can see that here. It's immediately brought to rest, okay, by the impact with the plane. The initial speed between P and the pulley, the initial distance between P and the pulley is such that in the subsequent motion, P does not reach the pulley. Okay, it's basically saying P just never ever goes all the way up the top here by the pulley, which helps us out in a way. Okay, show that the greatest height reached by P is 1.26 G. Right. Okay, so what on earth is going on here? So, as we discussed here, Q is moving down, and then it moves down to the floor here, and it moves with this distance here. If I call that distance, say, X, right? X meters, X distance. As we discussed at the start, because it's inextensible, this whole string, right? If Q moves down by some distance, P would move up by the same distance. Which means when Q hits the floor after X meters down, P would then be upwards by the same distance X. Okay? In the same time as well. X meters. Okay? So X for distance there. So I can say the distance here equals X. Okay, hopefully you can see that. I'll make it clear. Distance equals X. So as Q goes down by X, P would have to also move up by the same amount X. Hopefully that made sense. You with me here? So that's the distance P travels up after Q hits the floor. Okay. Actually, I'm not going to discuss what happens next. Let's just consider this. Let's just consider this first part then. So the part when Q starts at rest. So it starts at rest, right? Yes, because it's held at rest. So initially Q's at rest. So 0 speed. And also remember, again, the acceleration downwards the whole time is a third g, right? A third g for the acceleration. So actually we have enough information to work out this missing distance x in this time frame, okay? So if I use suvat down here then, if I do suvat down here, I want to work out this distance here, that q goes down in this time, okay? So, suvat at s, that is the distance I want to work out. That I'll call that x, right? U, initially it's at rest. V, I don't care about the speed at this point. A, deceleration is a third g, and t was 1.8 seconds, I believe. We were given that? Yes, 1.8. So, what equation does not involve v? Well, it's s is ut at a half at squared. So therefore, x is going to be 0 at a half of a third g, lots of 1.8 all squared. And so if I work that out, I get the distance x to be 0.54 g. Okay, I'm going to leave that in terms of g because my final answer needs to have a g in. Again, at this point, it is a good idea to leave g in rather than convert it to 9.8, unless you really have to, or if you really want to. So I'm going to leave it as g because my answer needs it in g. Okay, so I'm going to leave it as 0.54 g. Okay, so there we are. So by the way, I worked that out by literally I've just factored out the g at the very end, and then I just literally did a half times a third times 1.8 squared. That gets me 0.54, and then a g on the end. Okay, so that's my answer. So that is this distance here. Okay, this is 0.54 g. Now, as we discussed, if q goes down by 0.54 g meters, then p has to go up by 0.54 g. Okay, so we established now P originally starts here, then after up here somewhere, it's travelled 0.54 g. That's the same distance Q does until it drops down to the floor. Okay, so hopefully you're with me there. Now this is where it gets really complicated. Right, so if I just sketch again the sort of diagram what's happening with P, it's movement, right? If I sketch the movement, well, P is originally here, right? And so after it travelled 0.54 g meters up, it's now up here, okay? That's not the final distance where it's going to go up, okay? That is, so initially it's starting with 0 speed, and then it's going to have some speed v, okay? We could work out that speed, actually. But what I want to say what's going to happen is, after Q hits the ground, it obviously can't go down any further because it can't go through the ground, right? So what happens at that point, because Q can't go down any further, the string then becomes quite loose. Okay, so originally it's inextensible, but it's quite stretched out. Because the particles keep going down and up, it's stretching it. But the particles start kind of slowing down and stop moving where they are. So Q starts staying where it is down on the floor. The string no longer has stops becoming stiff, so it starts becoming really loose, what we call slack. Okay, which means when the string becomes loose, when one particle is not moving any further down, there's no more real force in the string anymore, so there's no tension, okay? Which means at this particular point here, when P here, at this point, that's when there's no tension in the string. The string becomes too loose, okay? So, what that means at this point is P. There's no tension pulling the string up, the particle up. There's no tension. It's still connected to string, but the string has no force in itself. So what happens is the only force acting on the particle at this point, when there's no tension anymore, the only force is its weight, and that is again, what's its weight? kmg, or 1.5 g, 1.5 mg, sorry. So what's going to happen is it's essentially going to be moving against gravity now. Because remember, when you're moving against gravity, only weight is what's affecting you, which is what we've got going on here. So what's going to happen is, if the particle at this point forward, it has some speed v, at this point the acceleration is going to be down by g. Okay, it's going to move against gravity when there's no more tension to keep the particle going up. So the particle is going up in its own accord against gravity now. Okay, and so that means when it travels, it's going to have to come to a stop at some point upwards. So after this amount of distance, I'll call this amount of distance, then it's going to go to 0 speed. Okay, because as we discussed, the greatest height where it doesn't move forward or move upward anymore. After that point, it's going to come back down. So that's gonna allow us to work out the greatest height. P goes upwards. Okay, so that's the idea. Okay, so there we are. Now. At this point, again, it's just Suvat again, but it really is helpful to sketch the movement of P, the positioning of P. So P, there we are. P will end up with 0 speed after its greatest height upwards. Okay, right. So if I want to work out this distance, then, well, I've got the acceleration that goes down by g. I've got the final speed. I've got the distance. I don't have time, so I'm going to have to work out this velocity after it reaches this point. If I want to work out v speed, then, where basically the string becomes so loose, right? How am I going to work out v? Well, I can go. Well, if I know that the at this point, right, initially the acceleration was a third of g, right? So this is the initial acceleration when there is tension in the string. But after the tension goes away, right, then the acceleration becomes g, because then we're just moving against gravity. Okay, there's no tension pulling it up, so just moving against its own weight. Right, so at this point, then I can work out v. Right, I can work out this final speed right here. The final speed if we start at 0 down here. So if I use Suvat, then firstly, so for this first half, right, this first half of the journey here, I can work out v, which will allow me to work out the upper distance here. Right, so again, the distance is 0.54 g, that's going up. U is initially 0, because again, everything is at rest initially. V is what I want to work out. A, the acceleration is going up by a third of g. And T, I don't care about. Actually, I'm given T. Remember, T is the same time here, 1.8 seconds. But I don't need to include it, really, because I've still got all the information I do need to work out v. But which formula does not include the t? Well, it's v squared is u squared at 2as. So v squared is going to be u squared, which is 0, add 2 lots of a third g, lots of 0.54 g. So if I work all that out, I get 0.36 g. And so if I square root that, I get, because that's v squared, right? If I square root that, therefore v is actually just 0.6 g meters per second. So now I can work out this speed here, there, okay, in terms of g, right? So that's the speed when when the system, the rope, the string no longer has tension. It becomes slack, because that's the time when Q hits the floor and it doesn't move any further down. Right, so now I can work out and consider the second portion of the journey of P. So this portion here, so I actually don't need this weight here. So if I just consider now the second half, when it's now going against gravity, because there's no tension anymore, just its weight, I can use survey again to work out the distance after there's no tension. So how the remaining height it goes up until it reaches 0 speed. Okay, so the initial, well, that's the distance I want to work out. U, well, as we worked out, is now 0.6 g. V is 0, and A is, well, if we're taking upwards as positive, the motion, again, it's against gravity going down, so it's going to be minus g, and T I don't care about. So again, I'm going to use V squared is U squared at 2AS, so that means 0 is going to be 0.6 g all squared, add 2 lots of minus g, lots of F, okay, S, okay, there we are. So if I rearrange this then, so I'm going to get, well, 0.6 squared is, again, 0.36, so I get minus 0.36 g squared. Don't worry about the g squared, because it will cancel with this g here. That's going to be minus 2gs. So now if I divide by minus 2g, so if I get rid of this now, therefore S is going to be minus 0.36 g squared over minus 2g. That would be 0.18 g. So this distance here is 0.18 g. And there we are. So that's the highest point of the particle. So now we're pretty much done now, right? Because now the greatest height reached by P above the plane. So this is the plane or the floor. So how high up has P gone from the ground to the floor? Well, think about it. From the floor to when they at the level they start off with, it's 0.54 g, right? So initially P is 0.54 above, right? So total distance is 0.54 g, right? So if I just add that, if I draw the floor on my diagram here, again P is initially 0.54 g up, and then P, that's when it starts in my pulley. Then obviously it moves up to this point here where there becomes no tension. That is not, again, 0.54 g. So if I add that on, and then this subsequent height, after then it moves against gravity when there's no tension, it goes up another 0.18 until it comes to rest. Okay, doesn't go any more higher. So if I add on 0.18, and hopefully I get what they want. 1.26 g meters, okay? And there we are, 1.26 g. That's the greatest height it's above, that P is above the floor, okay? And so there we are. We just added all these distances up that P goes up in, starting from the floor, or at the floor level, which is 1.26 g. So there we are. Okay, quite a nasty question. Okay, sometimes it might come up at the very end of the paper. You might get like a 6-7 marker, maybe something like this. Okay, I've seen it on a few 1 or 2 past papers. They might ask you a menacing final question like that, so you need to consider the greatest height in this way. Okay. Right, we're going to look at another question. Okay, so we've got this question here, and it's pretty similar to the last one, probably a tad bit harder, but it's the same sort of ideas. So again, I'm giving a bunch of information about this pulley. Again, the same sort of information. So if I just add on my forces first, again, it's going to be a weight pulling the things down. So the mass of B is 3, so it's 3g pulling it down. Likewise for A, the mass is M, so it's mg pulling it down, and the tension's acting up at either end to oppose to stretching downwards. Okay, I'm also giving some information about time it takes to descend and ascend. Okay, lastly, I'm going to add on my accelerations. So, which one's heavier? Well, I'm told that the mass of A, m, is greater than 3. So it's greater than the mass of B, so that means A is heavier. So A is going to want to move down. Okay, and that makes sense because it's talking about A descending. Okay, so it makes sense for A to go down here. Usually, you'd if you don't consider the masses, which one goes down. Usually, the question tells you which particle's going down anyway, and which one's going up. So usually, they help you out there. That's the acceleration. We don't know what that is. We don't know what it is yet. But again, if A is going down, then B is going to go up. Okay, with the same acceleration. That is, I think, everything for now. For part A, they want me to show that the acceleration of B as it moves up is 3.2. So again, we're just going to consider F equals ma. So if I do F equals ma for B, then if I resolve upwards, because B wants to move upright, so tension is the upwards force, take away its weight of 3g, is going to equal ma. Well, the mass is 3, so it's 3a. Okay, well, actually, I can't work out acceleration just yet because there's this t. I know what g is, right? It's just a number, it's 9.8. But t, I don't know the tension. If I maybe consider a then, perhaps, maybe that might help, I don't know. Now a is going down, right? Because it's heavier. So, if I resolve downwards, then the weight is pulling it down. The weight is mg. Take away the tension now pulling it up, equals the mass, which is ma, right? Again, I'm in a bit of a pickle because I have this unknown m as well. I need a to be an actual number. Okay, so a not in terms of t or m. So I'm a bit of a pickle to find a. So let's maybe look at the question to see anything else that might help me here. Right? Okay. So, we're told initially A is 2.5 meters above horizontal ground. Actually, if I just get rid of this, you can see that here. Okay. If I get rid of the forces, A, you can see, is 2.5 meters above the floor, right, above the ground. We're told the particles are released from rest, and after A descends for 1.25 seconds, it strikes the ground. So after 1.25 seconds here, so we know the distance is 2.5, right? But we also know the time when it hits the ground is 1.25 seconds. And that's really it. So I've got the time A hits the ground. I've also got the distance it takes until it hits the ground, which is 2.5. Right, hopefully you can see that. Hopefully with me here. I also know it's at rest. So actually, initially, there's no speed. So actually, to work out the acceleration, which is again going to go down with A meters per second, it's just a Suvat problem for part A. So if I do Suvat here then, if I consider part A and it's Suvat instead of just F equals ma here, so the distance it goes down is 2.5. U initially it's 0, right? The initial speed is 0 because it's at rest. V, I don't care about the final speed. The acceleration is what I want to work out, and T, the time is 1.25. Okay, so that's all the information given about A and its movement. So again, the equation that ignores V is S is ut at a half at squared. So 2.5 is 0 at a half of A, lots of 1.25 squared. If I simplify this, I get 2.5 is, well, a half times 1.25 squared is 25 over 32, lots of A. So therefore A is 2.5 divided by 25 over 32. And so if I work that out, And you can see I'm going to get a number here. So this is the right way forward. I get 3.2. Great. So 3.2 there. So actually I can add all that on. So now B is going to accelerate up by 3.2. And A is going to go down by 3.2. Okay, so that's my acceleration. So actually needed to back there, but you never know. It might still be helpful if to use these F equals ma equations, right? These two equations from F equals ma might still help, right? Might still help. Then it says in part B to find the tension in the string as A descends. Well, actually, as we just done, we've already worked out the force equations, these two here. So I can work out the tension. Well, actually, it's probably best to substitute it into this top equation because I have the only unknowns are T and A. Obviously, I know that G is 9.8. That's not an unknown. But I know what A is now. So if I do T minus 3G is 3A, therefore T minus 3G is 3 lots of 3.2. So therefore T is going to be 9.6 add 3G. Okay. Okay. It looks a bit weird with a 3G. I'm going to probably sub in 9.8 into here maybe. Because they want my answers to be... Because part A, my acceleration was a number. So I guess... I'm going to use G's 9.8 to get an actual number for T as well. As a decimal. So 9.6 add 3 lots of 9.8. That's going to be... 39 newtons, and there we are. That's my tension. Then in part C, it wants me to show that M is 65 over 11. Okay, so now I can probably resort to this equation here, right, for part C. So again, using F equals ma, you're probably going to need to do. So probably a word of advice is with these sort of questions, even if you're not told, just do F equals ma on the both particles. You're probably highly likely going to need to use them both. Okay, so if I use this equation now, the other force equation I've got, F equals ma. So mg minus t is ma. But I know what t and a are now. So mg, take away 39, is going to be ma. So it's going to be m lots of 3.2, right? So therefore, mg take away 39 is equal to 3.2m. So if I collect all the m's, I get m lots of, and I'm probably going to sub in 9.8 for g, because if we pay attention, my m has no g in it. It's just a numerical fraction, right? No g in. So if I sub g is 9.8 into here, so 9.8 take away 3.2 equals 39. I'm just solving for m. It's solving for m here. So that is 6.6m is 39. Therefore, m is going to be 39 over 6.6, which would be 65 over 11. And there we are. We got what they wanted. Then in part D it says state how you use this information to how you used the information that the string is inextensible. Again, inextensible means the acceleration of both particles has to be the same. So the acceleration of, what is it, P and Q? A and B, sorry, A and B. Of particles A and B are the same. Okay. Actually, I probably should be a bit more specific. The same in magnitude. Because the acceleration, remember, acceleration is a vector. It incorporates direction. Which means A and B, well, A is going down and B is going up. So the acceleration physically, the physical number for the acceleration is 3.2. That is the same. That's the magnitude, the physical number, but the directions are opposite. So technically, I know it's a bit pedantic, but the acceleration wouldn't be exactly the same of both particles because they're going in different directions. But the physical acceleration number is the same, 3.2. So we call that the magnitude. Okay. Then we're told when A strikes the ground, it does not rebound and the string becomes slack. So that's saying that if A starts here, then after it goes down 2.5 meters, it hits the floor. At that point, again, the string becomes slack. Okay, because A is not pulling the string down any further, so it doesn't go down. Any further. So the string starts to lose its force. So there's no more tension in the string. And so after that point, we're told after it becomes slack, particle B moves freely under gravity. Again, like the last question, until it becomes taut. So then until there becomes tension in the string once again. Right, so a little bit more complicated than the last question. So if I literally just consider the movement, the positions of B, like with the last question. So again, B, again, we have the floor here. B is some distance above the floor. I don't care what that distance is. I'm just saying it's above the floor, right? There we are. So I'll say that's B here. Now, we're told that when A strikes the ground, now think about it, when A strikes the ground, it's gone down by 2.5 meters. As we discussed, if one particle moves some distance, the particle has to move the same distance as well. So if A has gone down by 2.5 meters, B has to go up by 2.5 meters as well. So if I add that on to my sort of diagram for B here, it's going to go up by 2.5 meters, right? There we are. Then we're told at that point when B goes up by 2.5 meters, so when A then hits the ground, that means there's no tension. At this point then, there's no tension, right? I'll add that on, which means essentially it's starting to go against gravity, okay? So when there's no tension, there's only weight pulling it down, so it's kind of in free fall. So it's going to accelerate against gravity at this point, okay? So the acceleration is G downwards, right, against gravity. Right, and then as we discussed, okay, so eventually it's going to go to 0 speed, right? It's going to reach a maximum height. Okay, and then it'll start to come back down. So it's going to go up, and then it's going to come back down afterwards. It reaches its maximum height. So in other words, P goes. Let's say that's the highest point B, and then P is going to come back down on the string again. Anyway, so again, B starts at rest. We're told the whole system. Well, it starts at rest. It's released from rest. So the initial speed of B is 0, right? We also know that the initial acceleration we worked out to be 3.2. That's the acceleration with tension, right? So it's going to go up by 3.2 because P's going up. But then at this point with no tension, then P's just moving in the air. Well, not in, kind of in the air against gravity, okay? Because there's no tension effect in it. But that's the greatest distance it moves up, right? So that's the highest distance. But they've not asked us for the greatest distance. They've actually asked us for the time between where A hits the ground and the time when the string becomes taut. So actually, two things. Firstly, it wants the time. So the time where initially there's no tension, right? So this time here. But also the time from when there's no tension to when there is tension again. So when the string is taut. Which means, obviously, it got again, as we discussed, B goes up to a maximum height where it goes to 0 speed, and then it comes back down, right? But when it comes back down, there's still not necessarily any tension. But if you kind of think, if we look at this diagram here, let's say B's up here, If P then starts going down the string again, if P goes down and down and down here, eventually B is going to start tugging down on the string. So now then there'll be tension again, right? Hopefully you can visualize that, right? So if B is going down, it's down enough, it'll start tugging down on the string, and so then it'll create tension again. Okay, so that's the idea. So when it reaches again back to this point, then it's below the no tension threshold, so there become tension again. So it wants the time for when it starts at no tension to when it reaches the zero speed, and then when it starts at zero again, at zero speed going down, to then this point where it starts to get tension back. Okay, right, and again all of this will be against gravity here in this part of the journey. So I want this time here, these two different times. So I'm going to consider these into two different journeys. Okay, so two different suvats. Okay, so again, when there's no tension initially, right, B is at rest. Then when it moves 2.5 meters upwards, then it has a speed V. Okay, that's probably my best bet, is to work out what V is first. Okay, then that'll be my initial speed for this part of the journey when it goes from V to 0. So there we are. So right, so firstly, if I do suvat, where should I do it? Should I do it up here? Okay, so what I'm focusing on this very first part of the journey, right? Where B starts at rest and then it shoots up 2.5 meters to a speed of V with an acceleration of 3.2. So the distance is 2.5, right? The initial speed is 0. V is what I want to work out. A, well, the acceleration is up to 3.2, and I don't care about the time, because whilst I do want the time here and here, so that's the time between where there's no tension and then when the tension comes back, I don't want the time in this very initial part of the journey. That's not the time they want in particular. Anyway, so I can work out the initial velocity, because the time that the formula that excludes the t is v squared is u squared at 2as. So v squared is 0, add 2 lots of 3.2, lots of 2.5. So v squared is going to be 16. So therefore v, quite simply, is 4 then, if we square root. So that's telling me the speed B is at, where there's no longer becomes any tension, so when the stream becomes slack, that speed is 4. So now I can work out this sort of second part of the journey, where now the initial speed is 4 at the instant there's no tension in the string, to when it reaches its maximum height at the speed of 0. But I don't want the height, I want the time. So again, the acceleration is acting down by g, so now that's another application of suvat. So if I do that here, let's do it here. So s, I don't care about the distance. U, well, now u is 4. The final speed is 0, because again, at maximum height, it's at 0 speed. A, the acceleration is, well, initially we're going up, right? The motion is going up against gravity. So if it's against gravity, if these gravity acceleration going down, it would be the opposite direction, so minus g. And t is the time I want to work out. So that will involve v is u plus at. That's the formula without distance. So therefore 0 is 4 minus g lots of t. So therefore gt is 4. Therefore t is 4 over g. Now I'm probably subbing g's 9.8. So it's 4 over 9.8, which is 20 over 49 seconds. Okay, so that time, so this time here, that time here from when it starts to have no tension to when it reaches its maximum height and it doesn't go forward anymore. That's 20 over 49. Right, so then if we're considering this this final part where now it's going down from the greatest height to now the no tension level. So when the idea is when B goes underneath the no tension level, then there starts to become tension once again, right? So when B is at that level there, right? Now actually because of the whole thing is kind of symmetrical, right? Because the pulley and the string is inextensible, it's light, so the motion is consistent and symmetrical, right, all the way through, right? Which means that if the time taken from no tension to a greater height is this time here, it's the same time at the other end. So if T goes up from no tension, but in 20 over 49 seconds, then it also comes down back to the tension level in that same time. Okay, it's sort of symmetrical, the same distance it travels, the same speed, so this would be 4 as well. Obviously just different direction. Instead of going down up, it's going down. So actually the total time for when it's in the no tension zone, if you will, so then it starts having no tension to when it comes down to having tension again, it's just 2 lots of this. So the total time with no tension, let's say, is going to be 2 times 20 over 49. That's going to be 40 over 49 seconds. Okay, or as a decimal, 0.82 seconds to 2 decimal places, and there we are. Right, absolutely horrendous, disgusting question. I think probably would say, at least for AS mechanics, probably one of the most hardest topics, I would say. So this is like an A8, well, you don't get A star in A8, well, maybe A level, but this is definitely the top grade question. If you can nail this, what I've understood there, don't worry if you don't. It's a very tricky question. It's aimed for the very top grades. If you can understand how to answer that question the way I just sort of did, if it helps in any way, if you can understand to answer that, you'll be setting yourself up really well. But that's extremely difficult question, these final questions here. Okay, but there we are, right? Okay, so we're going to look at some exam questions. Okay, the main idea is the same. We're going to have our weights. So at Q, before even looking at the question, I know I'm going to be adding on my weights, firstly at either particle. So if it's Km for Q, then it's going to be Kmg for its weight, and tension acting up at P, and the weight of 2mg, right? Putting P down. So before I've been looking at it, that's my forces. Now, I'm told that K is less than 2. So that means Q is lighter than P. So P is heavier, so P is going to want to move down. So the acceleration at P will be down. And I'm told the acceleration is 5g over 7. Likewise, then Q is going to want to move up with 5g over 7 acceleration. Right, okay. Using the model, find in terms of M and G the tension in the string. So again, I'm going to use F equals MA for the both particles. Well, actually, the problem, if I was to pick Q, I can pick Q, that's fine. It has K in, but P, I have 2M. So actually P, I know it's mass in a way. So if I resolve at P then, so if I do F equals MA at P, well, if I resolve downwards, because that's where P is going, it's going down, then the downwards force, the weight is 2mg. Take away the tension acting up, That's going to be ma. Well, the mass of P is 2m times the acceleration of 5g over 7. Okay. And so we can find T here, the tension in terms of m and g. Okay. So 2mg take away T is, well, 2 times 5 over 7 is 10 over 7 mg. So actually then T is just going to be 2 mg take away 10/7 mg. That's going to be 4/7 mg. And that is my tension there. Okay. And then for part B, it says explain why the acceleration of Q also has magnitude 5g over 7. So Q is accelerating up by the same acceleration 5g over 7. Why are they the same? Why are the accelerations at P and Q number wise the same? It's again because of the string being inextensible. Okay. So that because the string is inextensible. That's literally what that means. The string is inextensible. The accelerations of both particles are effectively the same. They have the same magnitude, technically, right? Okay, then part C then says find the value of K. So now, well, what do you think? If we considered at P, if we did F equals ma at P, what we're going to do now? Do the same for Q, right? So if I can now consider Q here. So if I resolve, well, Q's going up. So if I resolve up, right? Then again, the tension is acting upwards at Q. Take away the downwards weight of kmg. That equals ma. Well, the mass of Q is km. So it's km lots of deceleration, which is 5g over 7. Okay, so then if I just deal with this equation, so actually, and also remember that T from part A, the tension was 4/7 mg, so therefore 4/7 mg take away kmg is 5 over 7 kmg. Okay, and so to get K then. Well, actually, what do you think I can do here? What is common to every single term in this equation? Mg, right? So if I divide by mg, I'll make my life a lot easier. I can divide by mg, right? Mg there, and mg there, and mg there. So I get 4/7, take away k equals 5/7 k. Now we get a simple equation to solve for k, right? So 4/7 then is going to be 1k add 5/7 k. That's going to be 12/7 k. And then to get k, I can divide by 12/7. So 4 over 7 divided by 12 over 7. And so if I do that, I get k to be a third. Okay, k is a third there. And there we are. So that's literally the question, right? All we had to do there was just F equals ma on both the particles. Okay. No more funny business after that. And that's really it. Because now in part D, it just wants me to say one limitation of the model. There's plenty you can say for this, right? It's to do with this here. So we've used a whole bunch of modelling assumptions. And you need to remember they're just assumptions. In real life, for example, the pulley would have friction as it as the string moves through the pulley. So the problem is the limitations are these assumptions here. The balls are modelled as a particle, which means in reality there would be air resistance. Remember, particle means not negligible or no air resistance effectively. That could be an issue. There'd be air resistance as it moves through the air. The string is light and inextensible. That means no mass. Same acceleration and same tension throughout. Now I want you to think, would the tension be always the same if one particle is heavier than the other? I think not, but there we are. And the pulley is small and smooth. So smooth again means tension is the same at both P and Q. So you can take your pick. All of these are possible limitations, okay? You can, but you only ask for one. Now, I guess what you could say is, just very simply, one limitation is the string modelled as light. Okay? I guess you could say in reality, the string would have mass. And that's all you need to say. Okay, so the limitations arise from the modelling assumptions we made here. So the pulley being smooth, the pulley being light, the string being light, the string being inextensible, and the particles are particles, so there's no air resistance and stuff like that. Okay, so there's plenty you could say there, right? I only asked for one. That's it. Okay, now we've got this question here. Right, so here we're told at one end of a string. Okay, so I'm not gonna read the whole thing again. We can just label our forces. So Q is gonna have its weight pulling it down, so it's gonna be 3m, lots of G, and P is gonna be 4 mg pulling it down, and again tension acting up. Okay. And so P, you can see, is heavier than Q because the mass of P is 4m, Q is 3m. So P is going to go down. With the acceleration, I don't think we're told acceleration here, so I'll just call it A. And Q then is going to go up as it's lighter. Okay. Right. Now, that's really it. It says the string. Okay, just a blah, blah, blah. It's at rest. Okay, the usual information, right? It says in part A, using the model, find in terms of M and G, the magnitude of the force exerted on the pulley. Right, so this is very similar to the first example we've looked at. So we're talking about the force on the pulley. So remember, there's also stuff happening at the pulley side of the end as well. So if I draw a sort of vertical line here to separate the particles from the pulley itself will have its own forces. Now, the drawing this little thing here on the top of it, because there's a hidden force, right? That's keeping the pulley up, but because of that force pulling the pulley, stretching the pulley up, it's stretching the string up, right? So the string is then going to have tension going down by the pulley. These two tensions again are the force exerted on the pulley, right, by the string. The force exerted by the string are these two tensions that act on the pulley. That's pulling the pulley down, okay? Now, that's what we want to work out. Effectively, we want to work out 2T. That's the force. If we add these two tensions, those are the two forces, the tension forces, acting on the pulley, that's pulling the pulley down by the string. We just want to work out 2T. So the hard thing is we just need to work out T then we can double it. Okay, so before we do that then, again, very, very wise to just do F equals ma on the both particles. So if we take P first, so P, if we resolve, P is going down because it's heavier. So if we resolve down, so then we get the downward force, its weight is 4 mg, take away the tension acting up, that's going to equal ma. Well, the mass of P is 4m, so it's 4m times the acceleration a. I don't know what T or a is, so I'm going to have to leave it there. And then for Q, again, Q is going up. So if I resolve upwards, then the tension is pulling the Q up, right? T take away 3 mg, so the weight of Q pulling it down. That's going to equal MA. Well, the mass of Q is 3M, so 3M, lots of A. So we get these two simultaneous equations, right? So I want to find T ultimately. So if I rewrite my equations down here, let's switch it around. Minus T add 4 mg, and then T minus 3 mg is 3 ma. Okay, so I ultimately want to find the tension, right? So these are simultaneous equations. So at this point, I'm just trying to find T. So ideally, I probably would want to eliminate A to just get T, right? But I don't think that's going to be quite nice, because what I can do instead is eliminate T quite easily, because I've got minus T on the first one and plus T on the second. If I add these two equations, I can get A straight away. Then I can substitute that in to get T that way. So if I add these two equations, well, minus T add T goes away. So then 4 mg take away 3 mg is just 1 mg. And then that equals 7 ma if I add them. Therefore, 7 ma is mg. So A is mg over 7m. Oh, mg over 7m. Well, the m's cancel, so I'm left with g over 7. And that's my acceleration. So now if I substitute A into either equation, let's say the second one, okay. So then T take away 3 of G is 3 ma, where A is G over 7, right? So then T take away 3 mg is 3/7 mg. So then if I add 3 mg on, so if I do 3 mg, add 3/7 mg, that's going to be 24/7 mg. And that's my tension, right? There we are. 24/7 mg. I can't do anything more with that. I can't find M. I'm going to leave it in terms of G. Oh, it says it here. Find in terms of M and G. So, okay, I need to leave G where it is. So, okay, that's my tension in terms of M and G. So, therefore, the force on the pulley, so the force exerted on pulley by the string is 2T, as we discussed. It's going to be 2T, so that's 2 lots of 24/7 mg, which is going to be 48/7 mg newtons there. Okay, so that's the force on the pulley by the string. So the string creates a tension. As you can see here, the two tensions either side pulling the pulley down. So it's 2T. Okay, that's the hard part. So that's 8 marks. Now, if you were just freaked out to say, oh God, what does the force on the pulley mean? Oh God, don't answer the question and lose 8 marks. Because the bulk of the question was just doing F equals ma on the two particles. You'd probably pick up a load of marks by that. If you're struggling with these questions, just do F equals ma on P and Q and you secure quite a lot of marks that way. Okay, that's the standard approach. Again, hopefully you just realise by now all the forces are always the same every time. Okay, I've labelled my force diagrams in exactly the same way every single question. Once you practice and see enough of these questions, it's the same method every time. Hopefully you start to pick up on that now. You might get a weird question like I've gone over, but even those, if you practice enough questions, you'll see all the possible type of questions I might ask for this. And actually, hopefully the video just cover basically all the scenarios I might ask to do with pulleys here. Okay, so yeah. So anyway, if you see something a bit weird, just try and work out what you do know. You might pick up some marks. Okay, so just do F equals ma on the two particles here. Now, then in part B, it says state one limitation apart from ignoring air resistance. Well, again, there's a bunch of them. Again, it's to do with the modelling assumptions. So For example, the string is light. In reality, the string would have mass, so it wouldn't be light. So limitation is the string is modelled as light. In reality, it would have mass. Hence, it would affect the accuracy, right, of my answer. Okay, so I've got one more exam question, and this is, again, you'll see the final part of the question is, again, quite vicious, very similar though. You'll notice, again, hopefully you start to notice the questions are kind of similar, right, with what they're asking. So, okay, again, I'm giving a bunch of information. Again, if I add on my forces, first of all, for Q, if it's 5M, it's going to be 5mg pulling it down. We've got a tension pulling it up. Again, tension at P pulling it up against its weight pulling it down. Well, if the mass is 2m, the weight is 2mg at P. Okay? And so really that's it. So what's it asking for part A? Write down an equation of motion for P and Q. Again, remember, equation of motion means F equals ma. Okay? That's all it means. So write down F equals ma for both P and Q. So what is it? It wants for P. So firstly, we start with P. Again, what am I for? If I where things are going to move down to? Well, Q, because it's heavier, it's going to want to go down. So the acceleration will be downwards here. Am I told acceleration? Nope. So I'm just have to leave it as A. And P then, because it's lighter, will want to move up instead. And there we are. That's my full annotation for now. So for P then, again, if I resolve upwards, because P wants to move up because it's lighter. So the tension force pulling it up, take away the weight of 2mg pulling it down equals ma. So it's 2m times the acceleration a. And that's literally it. And then for part 2, for Q then, if I resolve downwards, because that's F equals ma, that's where the acceleration is. It's going down for Q because it's heavier. So the downwards force, it's its weight, take away the tension force acting up, equals ma again. Well, the mass of Q is 5m, so 5m times a. And that's it. And that's 4 marks just for writing these two equations. Obviously, you're going to need to annotate the forces, like I've done there, but it's the same every time. So if you can do it quite quickly, you get 4 marks pretty quickly. But the question then lures you into a false sense of security, because now you've got this nasty part B for 7 marks. Very similar to the one of the nasty questions we've seen before. Then it says, find in terms of H only the height above the ground when P first comes to instantaneous rest. So H again, if I now get rid of my annotations, so again, if you've got a messy diagram, don't be afraid to just quickly resketch it if it's too messy to work with. But here I can just rub it out. But this H is the height. Okay, that's the H they're talking about. Right, so what's going on? So let's read the question now. So we're told the hanging parts of the string are vertical with P, okay, the heights. The system is released from rest. In the subsequent motion, Q does not rebound when it hits the ground and P does not hit the pulley. So that means when Q hits the ground, essentially, it doesn't rebound, so it doesn't go back up. So Q stays on the ground. So again, we've got this situation again where Q is going down. After it travels H meters downwards, it's on the floor. So again, we're going to be considering the heights of the H. No, not the heights. The heights when P goes up, not H. When P goes up, we're going to be considering the motion of P until its maximum again. So if I then draw a diagram for P, again, a good strategy for these sort of questions, if I have the floor here, P is initially 2h meters above. There we are. And then, if Q goes down by h meters to the ground, then P goes up by h meters in that same time. So P is up here, let's say, after h meters. Now, after that point, when Q hits the ground, as we seen before, there's no Q, it's not adding any more force on the string. The string loses its sort of tension, right? It becomes slack. The string becomes loose because Q refuses to move down any further, right? So there's no tension beyond this point when Q hits the ground. So this is the no tension level, if you will, right? So then at that point, when there becomes no tension, there's only weight. So P, when it hits up with this speed, after it travels h meters up, then it goes up against gravity. So the acceleration will be g downwards, right, against gravity, until it reaches this point with this distance up here, when it goes to 0 speed. Okay, so that's its maximum height. Okay, that's the maximum P goes up, and then P will come back down. Okay, now initially, again, P initially has no speed. So then after it travels h meters, it attains a speed of v. I don't know what v is. And then after that point, it travels up even further to then it gets to 0 speed again. So then it doesn't move up. It doesn't move up anymore. And so then, and again, this first part of the journey, so if P starts there, then if P starts here, there's tension up to this point. So the acceleration is what we worked out. Oh no, we haven't worked out. It's just A, right? It's A. So it's A. There. Okay. Now that acceleration is in this, these two equations here. Right, so actually I'm going to need to work out the initial acceleration before the tension is removed. So that comes from solving these two equations, right? So okay, I need to solve for A. So if I jot down my equations, so that's my first one. My second one is minus T. Add 5 mg is 5 ma. That's my second one. Well, I can get rid of T quite easily by adding these two to get the initial acceleration A. So then I get 3 mg is 7 ma. Therefore, 7 ma is 3 mg. So to get the acceleration, I can divide by 7m. So A is 3 mg over 7m. So it's 3/7 g, because the m's cancel, right? So there we are. So that means if we go up to this diagram here, the initial acceleration, where there's tension and everything, it's 3/7 g. And so there we are. So if we want to work out then the distance all the way up here, well, we can't do that at the moment because we're going to need this initial speed, this v, the initial speed v. So the initial speed after no tension. Right. So how are we going to do this? Well, if I then just consider the first part of the journey, so when initially it's 0 speed up to v. So if I do see that here, right? So I know initially it travels h meters up. Again, as we can see here, initially it starts here, and then after h meters it's gone up in, it ends up with this speed here. So initially it goes up by h. The initial speed is 0. U is 0. V is what I want to work out, because then if I work that out, I've got the initial speed for the second part of the journey after it starts having no tension. And then A, again, is 3/7 g. That's the acceleration with tension. And T, I don't care about. Okay, so then I'm going to need to use V squared is U squared at 2AS. So then V squared is 0 at 2 lots of 3/7 g times h. So V squared is 6 6/7 GH. Okay, this is quite awkward. So then that's V squared. So we need to square root that. So I'm just going to leave it as root 6/7 GH. Okay. So that's my speed. Again, it looks ugly, but that is my speed. Okay, that's the speed when it starts having no tension. So root 6/7 GH going up. Okay. There we are. Right, so now, if I now consider the second part of the journey, so here, right, where now I can get the distance, right? I don't know the distance, but I know the initial speed is now this root 6/7 GH. And you'll see why in a minute, why I don't need to be worried about the square root, because we're going to be squaring it again to get rid of the root. Okay, but V, I know at the end is 0. That's when it reaches maximum distance. And A, well, it's going against gravity, so if it's going up, then it's minus G, and T I don't care about. So again, I'm going to be using the same formula. V squared is U squared at 2AS, but now I want my distance. Well, V squared is 0, and U squared, well, if U is the root of all of this, then U squared gets rid of the root. So I'm just left with 6/7 GH. Add 2 lots of A, which is minus G, lots of S. So therefore, minus 6/7 GH is minus 2GS. So therefore, if I divide by minus 2G, I get S to be... Okay, so that's going to be... well, the G will cancel because you're dividing G by G. And so minus 6/7 divided by... I'll tell you what you can do. It looks a bit hard to sort of divide that, right? Let's break this down. Okay, let's not jump any steps. So what I want to do here to solve for S, I want to do minus 6/7 GH divided by minus 2G, right? Now, I can actually bring this as one fraction here to be minus 6GH on the top, right? And so actually then, we actually can convert this into KFC, keep flip change. So if I change it to a times, then do the reciprocal, so divide by times by 1 over minus 2G. So now we get minus 6GH over minus 14G if I times the top numbers and the bottom numbers, the numerator and the denominator. Well, now hopefully it's a lot clearer how we can get the simplified distance. So the G's will cancel, okay, and then minus 6 over minus 14, that goes to 3/7. So 3/7 H meters, okay. And so this is this distance here, 3/7 H. There we are. So we're pretty much done. So now it wants, in terms of H only, the height above the ground, so the height above the ground, to then when P comes to rest. Well, P comes to rest here, right? As we've discussed, when it reaches maximum height. So if we want the whole height starting from the ground up to this end point here, we need to add all these distances together. So that means the total distance P has travelled is going to be the initial 2H, right? Add H, and then add this 3/7 H. If we add all that together, so 2 add 1 add 3/7 is 24/7 H in meters. Okay. And so there we are. Okay, so these are very, very tricky questions, especially that sort of question. But again, if you're aiming for those top grades, hopefully you start to become more comfortable. with how I'm approaching that sort of question, by considering the motion as there becomes no tension, so it goes against gravity, and then up to maximum height where the speed at the end is 0. Okay, and so there we are. Then in part C, it wants me to now state one limitation of modelling the balls as particles. So what's the issue specifically with the balls as particles? Now remember, particles, what that means is it's basically a single point. Okay, so all the mass, everything to do with the particle, is all contained in an infinitesimally small point, a single point, right? Like a coordinate, right? On an XY grid. The other thing is, the particles means we ignore air resistance, and that's probably the more significant one. In reality, as it's moving through the air, especially as it's moving against gravity, air resistance will slow it down, so it will travel a smaller height up. Okay, so that's the limitation. Limitation is modelling the balls as particles means ignoring air resistance. In reality, there would be air resistance that slows them down. Okay, and so there we are. Then it says also in reality, the string will not be inextensible. State how this affects the accelerations. Okay. So in reality, the string would not be inextensible. Now remember, inextensible means the same acceleration. So if it's not inextensible, well, therefore the particles will not have the same acceleration. So it's as simple as that. Particles will not have the same, I'm going to say the same magnitude in acceleration, because again, I'm being very pedantic. Okay, they would accept just not the same acceleration, but I'm being a bit pedantic because I'm talking about the physical number of the acceleration. Yes, they're accelerating the same number, but they're going opposite directions, right? If you remember, one goes down, the other one goes up. So technically the acceleration isn't the same because it incorporates direction. They're going opposite directions, so it's not the same. But the number physically is. I'm talking about the number, the magnitude, okay? So I'm being quite specific there. And so there we are. So that is it. That's it for the first part of this. So hopefully now you start to become more comfortable with pulleys, particularly when the two particles are in the air. So when one particle comes down, the other one goes up the pulley. It goes up the string, okay? So that's it. I'll see you next time.